The light from these primordial galaxies has been stretched by the expansion of the universe, a process known as redshift. By analyzing this redshift, astronomers can estimate the distance and age of galaxies, essentially turning telescopes into time machines. What we see now is not what these galaxies are, but what they were eons ago, ghostly echoes from the deep cosmic past. Yet the mystery deepens. Some of these early galaxies appear too massive, too evolved, to fit within existing models of galaxy formation. They seem to defy the standard timeline, growing faster and earlier than expected. This forces scientists to reconsider aspects of cosmology itself. Perhaps dark matter played a more active role in early galactic evolution, or maybe the first stars formed in ways we do not yet understand. Indeed, these cosmic anomalies detected by Webb prompt deeper questions about our fundamental understanding of the universe's birth and evolution. One particularly intriguing puzzle is the rapid emergence of massive galaxies so soon after the universe's inception. Standard cosmological theories propose that galaxies grow gradually, merging and accreting matter over billions of years. Yet, Webb's observations challenge this notion, revealing giant galaxies formed remarkably early, only a few 100 million years post-Big Bang. This phenomenon suggests either the presence of an unknown mechanism driving accelerated galactic assembly or that the early universe had conditions conducive to a much faster growth of structure than previously believed. Astronomers speculate that these surprising observations might be explained by primordial clouds rich in gas and dark matter, denser and more massive than initially thought. Such conditions could dramatically speed star formation, leading to rapid galactic development. Another possibility involves the role of supermassive black holes at galactic cores. Early black holes could have acted as gravitational anchors, rapidly funneling matter inward, thus accelerating the growth of galactic structure and fueling intense periods of starburst activity. Furthermore, Webb has opened a new frontier in exploring galaxy collisions and mergers, events essential for understanding galactic evolution. When galaxies collide, their interactions stir gas clouds, triggering bursts of star formation that can illuminate whole regions. Observing infrared radiation, which penetrates dense cosmic dust clouds, JWST can capture these energetic events in exquisite detail, allowing researchers to observe galaxy mergers in unprecedented clarity. Such observations not only reshape our understanding of galaxy formation but also provide crucial insights into how our own Milky Way might have evolved. Scientists now believe that our galaxy experienced multiple mergers in its early history, a hypothesis supported by the complex stellar streams and populations found within its halo. By studying these distant collisions and mergers, astronomers can piece together the evolutionary paths that might have shaped galaxies closer to home. Adding another layer of complexity is the detection of organic molecules and chemical compounds within distant galaxies. Webb's powerful spectrometers have identified signatures of complex molecules in regions of active star formation, hinting at a chemical richness present from the earliest epochs. This discovery expands the potential timeline for cosmic chemical evolution, suggesting that the fundamental building blocks for life might have been widespread throughout the universe earlier than previously imagined. Webb's groundbreaking detection of these organic molecules, compounds rich in carbon, oxygen, nitrogen, and hydrogen, signifies more than just chemical complexity. It fundamentally reshapes our conception of cosmic habitability. The presence of these molecules in galaxies billions of years old hints that the chemistry necessary for life was established remarkably early in the universe. Such findings not only enrich our understanding of astrochemistry but also push scientists to explore the tantalizing possibility that life's molecular precursors are nearly ubiquitous, scattered across the cosmos long before planets like Earth ever existed. The telescope's spectroscopic instruments, such as NIR-SPEC, near-infrared spectrograph, allow astronomers to dissect the chemical composition of distant galaxies with unprecedented precision. Observations reveal intricate molecular signatures, including polycyclic aromatic hydrocarbons, PAHs, often regarded as critical precursors to the formation of life-supporting environments. These complex organic molecules are found within vast, dense clouds of dust and gas, stellar nurseries illuminated by newborn stars. Their discovery in such ancient cosmic structures points to sophisticated chemical reactions taking place at surprisingly early stages in cosmic history. Moreover, Webb's sharp eyes have also unveiled detailed glimpses into the environments around active galactic nuclei, AGN, regions dominated by supermassive black holes consuming enormous amounts of matter. These AGN are cosmic powerhouses, emitting intense radiation capable of triggering or suppressing star formation across entire galaxies. By probing infrared emissions deep within these dynamic regions, astronomers can examine the complex interplay between supermassive black holes and their host galaxies. This relationship, known as AGN feedback, has profound implications. Black holes may either stimulate or halt star formation, shaping galactic evolution in ways we are only beginning to fully comprehend. Further complicating this cosmic puzzle, JWST has provided clearer views of galaxy halos, enormous, diffuse envelopes of gas, dust, and dark matter surrounding galaxies. Far larger than previously imagined, these halos serve as vast reservoirs of matter, feeding star formation and influencing galaxy morphology. Studies suggest that galactic halos could harbor significant amounts of previously undetected baryonic, ordinary, matter, potentially solving part of the long-standing mystery known as the missing baryon problem. This elusive matter, now slowly coming into view, may help explain discrepancies between theoretical models and observations of cosmic structures. In addition, JWST's deep field observations continue to expand our cosmic horizon, pushing the observable universe further back in time. Galaxies once considered the very limit of observational capabilities now appear clearly, revealing structures and star formation rates that challenge our current cosmological models. Particularly astonishing are the dense clusters and protoclusters of galaxies JWST has uncovered at extreme redshifts, well beyond any previously observed. These immense structures emerged incredibly early, suggesting that large-scale cosmic web formation, the interconnected filamentary network of matter permeating the universe, began sooner and progressed more rapidly than theoretical predictions anticipated. These findings necessitate refinements in cosmological simulations, including improved models of dark matter's gravitational role. The dark matter scaffolding, thought to underpin cosmic structure formation, must have been established swiftly and efficiently to facilitate the accelerated growth of these massive early clusters. Webb's data thus compel cosmologists to revisit assumptions about dark matter's distribution, density fluctuations, and interactions with ordinary matter in the early universe. Furthermore, JWST's capacity to peer through dust clouds illuminates previously obscured phases of galaxy evolution. Massive, dust-enshrouded galaxies, previously invisible to optical telescopes, now emerge vividly, revealing unexpectedly vigorous star formation hidden behind thick curtains of cosmic dust. The presence of these dust-obscured galaxies, dogs, at such ancient epochs implies that galaxies rapidly enriched themselves chemically, synthesizing heavy elements and dust much faster than expected. This rapid enrichment is likely due to prolific early generations of massive stars, whose explosive supernova deaths seeded their environments with heavy elements, fueling further star formation and planetary system development. The implications of this early chemical enrichment ripple outward toward understanding planetary formation processes themselves. Webb's findings suggest that exoplanetary systems could have formed far earlier than astronomers previously suspected, potentially even around the first generations of stars. Thus, the window for planetary, and perhaps biological, evolution in the cosmos has widened dramatically, shifting our understanding of when and how habitable conditions might have arisen in the universe. These discoveries carry deep philosophical implications as well. By revealing that the cosmic conditions necessary for life emerged swiftly and abundantly, JWST challenges us to reconsider our place in the universe, not as an improbable anomaly, but as a natural product of universal processes occurring across space and time. We begin to see our existence as intimately connected to the fundamental laws of physics and chemistry that govern the universe from its earliest moments, inviting profound reflections on the cosmic context of life itself. The journey of discovery led by Webb continues to unfold, promising not only new scientific breakthroughs but also a deeper comprehension of the universe's complexity, beauty, and potential for life. As humanity gazes ever further into the cosmic dawn, each new observation challenges established paradigms and enriches our cosmic perspective, compelling us toward a more profound understanding of our own origins within the vast tapestry of the universe. JWST's unprecedented ability to capture details across vast cosmological distances continues to reshape our comprehension of the very fabric of the universe. One particularly intriguing development arises from its observations of cosmic reionization, the epoch when the universe transitioned from opaque darkness into transparency, as the first stars and galaxies flooded their surroundings with energetic ultraviolet radiation. This process, occurring within roughly the first billion years after the Big Bang, stripped electrons from neutral hydrogen atoms, illuminating the cosmos and forever altering its structure and visibility. By precisely measuring the signatures of early galaxies, JWST has allowed astronomers to probe deep into this transformative era, reconstructing in detail how the universe awoke from its primordial darkness. Surprisingly, JWST data indicates that reionization began earlier and proceeded more rapidly than previous observations had suggested. The early galaxies responsible appear exceptionally luminous and productive, their populations of massive stars efficiently ionizing vast regions of intergalactic space. This suggests a fundamentally different composition and stellar structure for these primordial stars, often referred to as population 3 stars. These hypothetical first-generation stars, formed entirely from hydrogen and helium produced in the Big Bang, may have been extraordinarily massive, short-lived, and incredibly luminous, generating intense radiation that drastically influenced their surroundings. Although direct observations of population 3 stars remain elusive, Webb's detection of extremely distant galaxies provides indirect clues to their existence. The unusual brightness and high-energy output of these early galactic systems strongly imply they contain stellar populations different from any known today, fueling renewed theoretical modeling to predict their properties. Thus, JWST has opened new avenues to search for these elusive celestial ancestors, guiding astronomers toward more sophisticated interpretations of stellar evolution in the universe's infancy. In parallel, Webb's infrared instruments have offered new insights into the elusive nature of dark matter, the invisible substance accounting for roughly 85% of all matter in the universe. By precisely measuring the distribution and motion of visible matter within distant galaxies, astronomers can infer the gravitational presence and behavior of dark matter. Webb's observations reveal subtle but significant variations in galactic rotations and gravitational lensing effects that suggest new complexities in dark matter distribution. For instance, some early galaxies seem less influenced by dark matter than predicted by standard models, raising questions about how dark matter structures initially formed and evolved. Alternatively, these discrepancies could hint at entirely new physics, potentially requiring revisions or expansions to the fundamental cosmological model known as lambda-CDM, lambda-cold dark matter. Additionally, JWST's deep imaging capabilities have profoundly expanded our understanding of cosmic voids, vast, relatively empty regions in the cosmic web. Previously considered barren spaces between galaxy filaments, these voids have been shown to contain subtle yet intriguing structures, faint dwarf galaxies, and tenuous threads of gas previously invisible to astronomers. This discovery emphasizes the interconnectedness of all cosmic regions, highlighting how even seemingly empty spaces influence cosmic evolution and structure formation. Such findings demand a re-examination of cosmological models that incorporate a deeper understanding of the delicate interplay between voids and galaxy clusters. Simultaneously, JWST's refined view of stellar nurseries in galaxies closer to us, such as in the Orion Nebula or the Large Magellanic Cloud, has significantly enhanced our comprehension of star formation processes. Detailed infrared observations uncover intricate structures, protostellar disks, protoplanetary rings, bipolar jets streaming from young stars, and complex interactions between forming stars and their dusty environments. Webb's high-resolution imagery has even identified early planetary systems in formation, unveiling clues about the fundamental processes guiding planetary formation. Such insights allow scientists to piece together how solar systems similar to our own might form, evolve, and eventually harbor conditions suitable for life. Moreover, JWST observations have begun reshaping planetary science itself. Exoplanetary atmospheres, previously difficult to analyze thoroughly, are now being characterized with unprecedented clarity. Webb spectroscopy provides detailed atmospheric signatures of distant exoplanets, revealing water vapor, carbon dioxide, methane, and even trace gases that could indicate biological or geological activity. By examining worlds orbiting stars beyond our solar system, JWST not only informs our understanding of planetary habitability but also advances the search for extraterrestrial biosignatures, significantly progressing humanity's quest to discover life elsewhere in the cosmos. The philosophical implications of these findings extend further, offering a profoundly altered vision of humanity's place within the universe. Webb's revelations about the ubiquity of complex molecules, the accelerated emergence of galaxies, and the diverse conditions conducive to life foster an image of a cosmos richly capable of supporting complexity. Humanity's existence thus appears increasingly less isolated, reinforcing a view of life as an integral outcome of the cosmic evolutionary process rather than a mere anomaly. As JWST's observational campaign continues, each new revelation reshapes our cosmic narrative. Every image, spectrum, and data set not only deepens scientific understanding but also challenges humanity's imagination, compelling us to reconsider fundamental aspects of cosmology, planetary science, chemistry, and astrobiology. The discoveries of this telescope embody the essence of human curiosity and the endless pursuit of understanding, a quest pushing the boundaries of knowledge and redefining our cosmic identity. With JWST pushing the frontiers of observational cosmology, another exciting avenue of research emerges, understanding the influence of magnetic fields on cosmic structure formation. Although magnetic fields have long been known to exist within galaxies, their precise origin and role in early cosmic evolution remain deeply enigmatic. JWST's sensitive infrared instruments have begun to indirectly probe these ancient magnetic structures by observing polarized light scattered and emitted from distant, dust-rich galaxies. These subtle polarization signatures provide astronomers crucial clues about how magnetic fields influence gas dynamics, regulate star formation, and possibly shape the evolution of galaxies themselves. Indeed, recent analyses suggest that early galaxies possessed surprisingly well-organized magnetic fields, contrary to expectations that primordial magnetic fields would be weak and chaotic. Such well-structured magnetic fields could have facilitated the rapid collapse of gas clouds into stars and may even have influenced the rate and efficiency of early galaxy growth. This observation compels astrophysicists to explore new theoretical frameworks explaining how such magnetic fields were generated shortly after the Big Bang, perhaps through turbulence in the primordial plasma, cosmic inflation processes, or early star formation itself. Webb's discoveries thus initiate a fundamental shift in our understanding of magnetohydrodynamics at cosmological scales. Alongside these revelations, JWST's infrared eyes have shed new light on the phenomenon of gravitational lensing, nature's own cosmic magnifying glasses. Massive foreground galaxies or galaxy clusters warp the fabric of spacetime, bending and amplifying the light of more distant galaxies behind them. Webb has harnessed these gravitational lenses to peer even deeper into cosmic history, uncovering galaxies so faint and remote that they were entirely undetectable with previous telescopes. Such gravitational lensing not only expands observational horizons but also provides precise tests for Einstein's theory of general relativity on unprecedented cosmic scales, potentially uncovering subtle deviations from our current gravitational understanding. Gravitational lensing also grants astronomers rare opportunities to measure the masses and distributions of dark matter within galaxies and galaxy clusters. By analyzing the lensing distortions captured in JWST's detailed images, scientists can map dark matter's invisible architecture in 3 dimensions, revealing intricate filamentary structures that underpin cosmic evolution. These precise maps offer powerful new constraints on theories of dark matter, potentially illuminating the particle physics underlying this mysterious substance, thus bridging cosmology and fundamental physics. Furthermore, JWST's examination of stellar evolution at various cosmological epochs highlights profound differences in stellar populations across cosmic time. Early galaxies observed by Webb often contain dense clusters of massive, short-lived stars, differing significantly from the relatively calmer, more stable stellar populations of contemporary galaxies. Such observations provide new insights into the earliest stellar life cycles, including massive supernova explosions, gamma-ray bursts, and neutron star mergers, all events that profoundly influence chemical evolution and galactic environments. Intriguingly, Webb's observations extend even into the enigmatic phenomena surrounding stellar remnants, such as black holes, neutron stars, and white dwarfs, illuminating their roles in galaxy ecology. For instance, JWST's detailed spectroscopy has detected dust and heavy elements in the aftermath of neutron star collisions, events crucial for synthesizing elements heavier than iron, including gold and platinum. These findings enhance our understanding of nucleosynthesis, the cosmic alchemy responsible for the creation of elements, and provide vital clues about how essential elements for life became abundantly distributed across galaxies. On the planetary front, Webb's in-depth studies of exoplanetary atmospheres also raise exciting possibilities for future observations of Earth-like worlds. By detecting subtle atmospheric signatures, Webb has begun identifying potential biomarker molecules, chemicals whose presence could indicate biological processes. Methane, oxygen, ozone, and complex organic compounds detected in the atmospheres of distant planets could hint at biological activity or prebiotic chemistry, allowing astronomers to refine methods to search for extraterrestrial life in future exploratory missions. Moreover, JWST's exploration of icy moons and asteroids within our own solar system provides significant comparative data for astrobiology. Observations of Europa, Enceladus, Titan, and even distant Kuiper belt objects offer new insights into subsurface oceans, complex organic chemistry, and habitability conditions. These studies not only enhance our understanding of life's potential distribution within our planetary neighborhood but also contextualize broader searches for habitable worlds across the galaxy. Philosophically, these cumulative discoveries compel humanity to reconsider profound questions about our identity and purpose within a boundless universe. Webb's exploration of the cosmic frontier challenges the anthropocentric perspective, replacing it with a vision of life as an intrinsic and perhaps widespread phenomenon, governed by universal physical laws and chemical processes. This perspective inspires deep contemplation on the nature of consciousness, existence, and the remarkable continuity linking humanity to the farthest reaches of space and earliest epochs of cosmic history. Ultimately, the ongoing scientific quest driven by JWST represents humanity's profound and enduring desire for knowledge. With each new discovery, we come closer to comprehending the grand cosmic story, how galaxies are born, stars live and die, elements form, and life emerges. Each revelation not only expands our scientific horizons but also enriches our shared understanding of the universe's beauty, complexity, and interconnectedness. As JWST continues peering deeper into the cosmos, humanity moves steadily toward a greater cosmic awareness, forever reshaping our perception of the universe and our place within it. As JWST further sharpens humanity's cosmic vision, astronomers also grapple with profound new mysteries related to cosmic entropy and the ultimate fate of the universe. Webb's precise measurements of distant galaxies, galaxy clusters, and cosmic structures provide invaluable data for studying entropy, the gradual increase of disorder, on unprecedented cosmological scales. By examining the evolving distribution and energy dynamics of matter and radiation across vast stretches of spacetime, scientists can now refine their understanding of how entropy governs cosmic evolution, potentially unveiling deeper insights into the universe's irreversible journey toward eventual equilibrium, often called heat death. These detailed observations by JWST underscore the role entropy plays in cosmic phenomena, from galaxy formation to black hole growth and star formation efficiency. For example, the energetic outflows from active galactic nuclei and starburst galaxies distribute energy and matter into intergalactic space, significantly influencing local and cosmic entropy balances. JWST's infrared capabilities have enabled researchers to observe directly these energetic winds, revealing their widespread presence even in very early galaxies. This data informs new models of entropy-driven feedback processes, altering our understanding of the fundamental thermodynamic forces shaping the cosmos. Additionally, JWST's exploration of the most distant observable regions raises fascinating questions about cosmic isotropy, the assumption that the universe appears uniform in all directions. Deep field observations sometimes reveal subtle anomalies or unexpected alignments among distant galactic structures, challenging the idea of uniformity at vast scales. Although these anomalies might initially appear minor, they carry potentially profound implications. Could they indicate undiscovered fundamental physics, relic effects from cosmic inflation, or perhaps even evidence of multidimensional cosmologies or interactions with parallel universes? Indeed, Webb's observations increasingly encourage cosmologists to test alternative theories, including variations on standard inflationary cosmology and multidimensional spacetime frameworks inspired by string theory and quantum gravity research. Such innovative theoretical developments aim to reconcile anomalies detected by JWST with our existing cosmological models, bridging observational astrophysics and theoretical physics in unprecedented collaboration. Moreover, JWST's detailed infrared imaging facilitates unique studies of cosmic dust evolution across time. Dust, comprising microscopic grains of silicates, carbon, and ice, plays a crucial role in star and planet formation, chemical evolution, and even the thermal balance of galaxies. Webb's observations reveal unexpected quantities of dust in galaxies formed soon after the Big Bang, indicating rapid cycles of dust creation and destruction. This rapid cycling demands new models of dust chemistry and supernova processes, prompting astronomers to reconsider how elements necessary for life were dispersed so efficiently throughout the early universe. Furthermore, by capturing detailed images of circumstellar disks, the birthplace of planets, JWST allows astronomers unprecedented glimpses into the formation processes of exoplanetary systems. Observations reveal complex patterns of dust and gas rings, spirals, and gaps, sculpted by forming planets or dynamic gravitational interactions. Such precise imaging of planet formation environments not only enriches our understanding of planetary origins but also provides invaluable context for interpreting our own solar system's development. In fact, JWST has begun exploring comets and asteroid populations within our solar system itself, studying their chemical compositions with unprecedented sensitivity. These celestial bodies serve as ancient cosmic archives, containing preserved materials from the solar system's earliest stages. By examining their molecular structures and isotopic signatures, astronomers gain direct insights into conditions existing billions of years ago, potentially illuminating the origins of Earth's oceans and even the ingredients of life itself. On a larger philosophical scale, JWST's discoveries encourage us to rethink our own cosmic narrative. The telescope's revelations about entropy, chemical complexity, and the universality of physical laws provide a powerful backdrop for contemplating human existence within this vast cosmos. These insights prompt reflections on interconnectedness, not only among cosmic processes but also between humanity and the universe that gave rise to it. The narrative revealed by JWST underscores a profound unity between the microscopic chemistry of life and the macroscopic evolution of galaxies, stars, and planets, binding all existence into a coherent cosmic story. Ultimately, as JWST continues its journey into the unknown, every observation becomes another step in humanity's quest to understand the cosmos more deeply, to decipher our origins, and perhaps to uncover hints of our shared cosmic destiny. The telescope, thus, is more than a scientific instrument. It embodies humanity's collective curiosity, our aspiration to explore, and our persistent pursuit of understanding. In exploring the farthest reaches of the universe, JWST enriches both scientific knowledge and human imagination, shaping how we perceive ourselves within the grand cosmic narrative that surrounds and defines us. Beyond cosmological mysteries and planetary origins, JWST's detailed observations are reshaping our understanding of cosmic time itself, an elusive dimension intertwined intricately with space, matter, and energy. By examining distant galaxies as they appeared billions of years ago, JWST effectively traverses the arrow of time, allowing humanity to witness stages of cosmic evolution otherwise forever lost. Each photon captured is a traveler from the distant past, offering insights into how cosmic structures evolved, how stars matured, and how galaxies emerged from primordial chaos into ordered forms. These observations reveal fascinating variations in galactic evolutionary pathways. Some distant galaxies observed by JWST evolved rapidly, forming stars at explosive rates, while others exhibited slower, more stable growth. This diversity suggests that cosmic evolution may follow multiple pathways influenced by subtle initial conditions, environmental factors, or variations in dark matter distribution. Understanding these different trajectories offers profound insights into the delicate interplay of gravity, dark matter, gas dynamics, and radiation that shapes galaxies across cosmic epochs. Moreover, JWST's refined views have exposed intricate, filamentary structures within galaxy clusters and intergalactic space, illuminating the web-like cosmic structure known as the cosmic web. These immense filamentary threads, comprised of gas, dark matter, and faint galaxies, connect distant galaxy clusters, channeling matter and energy across vast distances. JWST's sensitive infrared eyes reveal this structure more clearly than ever before, demonstrating that galaxies are not isolated islands but interconnected nodes within an extensive, dynamic network. Such discoveries emphasize the fundamentally relational nature of cosmic structures, suggesting that galactic evolution cannot be fully understood without considering their environment within the cosmic web. Additionally, JWST's observations increasingly challenge our notions of the boundary between life and non-life in the cosmos. The widespread detection of complex organic molecules and prebiotic chemistry in distant galaxies and planetary systems suggests that the universe is inherently predisposed toward complexity and perhaps even life itself. This chemical universality invites a paradigm shift, away from viewing life as an improbable cosmic accident, and toward recognizing it as an intrinsic consequence of universal physical and chemical laws. JWST thus encourages us to revisit fundamental biological and philosophical questions. Could life's emergence be inevitable, given suitable conditions? And if so, how widespread might life truly be across billions of galaxies? As JWST enriches our vision, it simultaneously reshapes our philosophical relationship with the universe. By capturing images of objects billions of years old, the telescope vividly underscores humanity's place in a vast temporal and spatial continuum. Seeing galaxies and stars from the earliest moments of cosmic history profoundly affects human understanding of time, existence, and our transient but meaningful place within an ever-changing universe. These images, by visualizing the deep past, invite humanity into a broader cosmic perspective, an invitation to see our history, present, and potential futures as intimately connected with the universal story. In this context, JWST's exploration goes beyond science. It touches upon humanity's collective consciousness and imagination. It invites us to perceive the universe not merely as something external to us, but as something that shaped us profoundly, chemically, biologically, and existentially. The cosmos is thus no longer distant and impersonal but intimately related to our origins, our nature, and our destiny. Finally, as JWST continues probing deeper cosmic frontiers, every observation expands our vision and comprehension of reality. The telescope embodies human curiosity at its finest, reflecting a ceaseless yearning to know more, see farther, and understand better. In unveiling the mysteries of distant galaxies, star formation, cosmic structure, entropy, dark matter, and potentially life itself, JWST does more than just reveal cosmic secrets. It enriches humanity's collective story, shaping our identity within the universe. As we peer ever deeper into space, we uncover the universe's wonders, ultimately discovering profound truths about ourselves along the way. The revelations provided by JWST continue to ripple through astrophysics, astronomy, astrobiology, and even fundamental physics, pushing the boundaries of what we previously thought possible. As Webb continues to peer into cosmic darkness, we are steadily unraveling a complex tapestry woven by gravitational interactions, energetic phenomena, magnetic fields, chemical evolution, and perhaps, life itself. Each discovery redefines how we perceive the universe, constantly reminding us that our understanding of reality is always evolving, driven by new data and fresh insights. A particularly fascinating frontier that JWST has begun to explore involves the study of transient cosmic events, such as gamma-ray bursts, GRBs, stellar explosions, supernovae, and kilonovae, the violent aftermath of neutron star collisions. By capturing the infrared signatures of these cataclysmic occurrences, JWST sheds new light on the mechanisms underlying some of the universe's most powerful phenomena. Gamma-ray bursts, for instance, represent some of the most energetic explosions in existence, occurring when massive stars collapse into black holes or neutron stars collide, producing extraordinary flashes of energy observable from billions of light-years away. JWST's infrared observations reveal previously hidden dust clouds and chemical enrichments accompanying these spectacular events, enabling scientists to decode the detailed physics behind such violent cosmic dramas. Further, JWST's detection of distant stellar explosions helps astronomers refine our understanding of cosmological distances. Supernovae, serving as standard candles, allow precise measurement of cosmic expansion rates, critically important for cosmology. Webb's high-resolution observations of these distant supernovae offer detailed insights into the expansion history of the universe, allowing astronomers to test and refine theories explaining mysterious phenomena like dark energy, the enigmatic force accelerating cosmic expansion. By providing clearer measurements of cosmic expansion rates, JWST may help resolve existing discrepancies, such as the Hubble tension, a puzzling mismatch between locally measured expansion rates and those inferred from cosmic microwave background observations. JWST also offers remarkable opportunities to test and refine theories of fundamental physics, including the nature of gravity itself. Observing gravitational lensing effects around massive galaxy clusters and black holes allows astronomers to conduct stringent tests of Einstein's general theory of relativity on unprecedented scales and precision. Some early JWST observations suggest subtle anomalies or deviations in gravitational lensing patterns, which, if confirmed, could point toward new gravitational physics or modified theories of gravity. These possibilities excite physicists, as even slight deviations from general relativity could imply entirely new fundamental physics, potentially leading to breakthroughs in quantum gravity or multidimensional theories. Additionally, Webb's sensitive instruments permit astronomers to peer into extreme cosmic environments, such as the vicinity of active galactic nuclei or the energetic accretion disks around black holes, with extraordinary clarity. By studying these environments, astronomers gain insights into the physics of matter under extreme gravity and intense radiation conditions, phenomena impossible to recreate on Earth. Such studies help illuminate fundamental questions about black holes, event horizons, and relativistic physics, deepening our understanding of cosmic phenomena at the edge of scientific knowledge. Moreover, JWST's ability to investigate chemical processes in both distant galaxies and local planetary systems provides fresh insights into cosmic chemistry and its implications for life's origins. Detailed observations of chemical interactions within protoplanetary disks, cometary nuclei, and interstellar clouds reveal complex molecules, amino acids, and prebiotic chemical processes far more widespread and efficient than previously imagined. The universality and rapidity of this chemical complexity suggest that life's chemical precursors are abundant and perhaps inevitable, dramatically expanding the potential for extraterrestrial habitability throughout our galaxy and beyond. Philosophically, JWST's findings encourage profound contemplation about humanity's place within the universe's expansive timeline. As we look billions of years back in cosmic history, witnessing galactic births and stellar deaths, we become keenly aware of our fleeting yet profoundly interconnected existence within the cosmic narrative. JWST's observations, capturing ancient photons that began their journey long before our solar system even formed, deepen our appreciation for our transient but meaningful existence, a brief moment within an unimaginably vast cosmic drama. Each discovery made by JWST thus enriches human knowledge not only scientifically but also existentially. As the telescope continues revealing the universe's secrets, we gain a deeper sense of wonder, humility, and interconnectedness. Humanity's exploration of the cosmos through JWST represents far more than scientific inquiry. It embodies our innate desire to understand ourselves and our place within the greater cosmos, continuously inspiring awe, curiosity, and contemplation about the profound mysteries that surround and sustain us. Ultimately, the James Webb Space Telescope stands as one of humanity's greatest achievements, a testament to our curiosity, ingenuity, and relentless pursuit of knowledge. Each observation peels back another layer of the cosmic mystery, revealing new puzzles and profound insights that challenge and refine our understanding of the universe. From distant galaxies and enigmatic black holes to the chemical complexity underpinning potential life, JWST's revelations bridge the microscopic and macroscopic realms, binding the story of atoms and molecules to the grand narrative of galaxies and stars. In this extraordinary journey, we have glimpsed not only the distant reaches of space but also our own origins reflected in cosmic processes. Webb's discoveries remind us of a profound interconnectedness, across space and time, matter and energy, life and the universe itself. Through its gaze, we recognize ourselves not merely as passive observers but as active participants in a cosmos still unfolding, continuously evolving toward greater complexity and wonder. As JWST continues exploring the depths of the universe, the discoveries it enables will continue to inspire humanity's collective imagination, challenge our fundamental assumptions, and deepen our appreciation for our existence. This powerful telescope has forever changed how we perceive our place in the cosmos, revealing a universe far richer, more dynamic, and more intricate than we ever dared to imagine. As we continue to look outward, guided by JWST's vision, we also look inward, better understanding who we are and our profound connection to the vast, beautiful, and mysterious universe we call home. NGC 1300 continues to captivate astronomers with its intricate structure and the secrets it holds about the mechanisms driving galactic evolution. Its well-defined barred structure is a focal point for studying the transport of gas and angular momentum. The bar acts as a cosmic conveyor belt, guiding interstellar material toward the central regions where it accumulates, igniting bursts of star formation. This process is further evidenced by the glowing, clumpy regions along its spiral arms, teeming with young, luminous stars. The nucleus of this galaxy presents another layer of intrigue. Observations have revealed a tightly bound nuclear ring encircling the core, composed of vibrant, star-forming regions. These rings are thought to arise from the complex interplay of gravitational forces within the bar and the spiral arms, funneling gas into specific regions where it collapses to form stars. This nuclear activity offers a glimpse into how galactic cores evolve and sustain themselves over time. NGC 1300's bar also plays a role in shaping the overall rotation curve of the galaxy. Unlike simple disk galaxies, barred spirals like this one exhibit unique rotational dynamics, with the bar influencing the motion of stars and gas across the galactic plane. By studying these dynamics, astronomers gain valuable insights into the role of gravity in dark matter in maintaining the stability of such systems. Dark matter, though invisible, is a critical component of NGC 1300 structure. The motion of stars and gas indicates the presence of a massive dark matter halo that extends far beyond the visible galaxy. This unseen matter is crucial for explaining why the galaxy's outer regions rotate as rapidly as they do without flying apart. Understanding the distribution of dark matter in galaxies like NGC 1300 provides important clues about the nature of this mysterious substance that dominates the universe. Another fascinating aspect of NGC 1300 is its environment. Situated in the constellation Eridanus, it resides in a region of the sky populated by other galaxies. These neighboring systems may exert subtle gravitational influences on NGC 1300, potentially shaping its structure over billions of years. Such interactions, whether through close encounters or long-range gravitational effects, are key to understanding how galaxies evolve within their cosmic neighborhoods. NGC 1300 size is another remarkable feature, with its diameter stretching approximately 110,000 light-years, making it comparable to our own Milky Way. This immense scale allows astronomers to study the galaxy as a microcosm of the larger universe, with processes such as star formation, gas dynamics, and the effects of dark matter all playing out within its borders. Each of these processes offers a piece of the puzzle for understanding the broader mechanisms governing galaxies throughout the cosmos. Observations of NGC 1300, particularly through high-resolution imaging from instruments like the Hubble Space Telescope, have revealed additional structural details. Faint outer regions of the galaxy, including extended spiral arms and possible tidal streams, suggest a dynamic history involving past interactions or mergers. These features provide clues about the galaxy's past and the forces that have shaped it into the majestic structure we observe today. Under continued observation, NGC 1300 reveals itself as an unparalleled example of galactic complexity and beauty. Its spiral arms, extending symmetrically from the bar, showcase intricate patterns of star-forming regions. These arms are not just visually stunning but also act as laboratories for studying the physical conditions that drive the birth of stars. They contain vast amounts of gas and dust, the raw materials for star formation, interspersed with clusters of young, hot stars that illuminate their surroundings. The galactic core of NGC 1300 also provides a unique opportunity to explore the behavior of supermassive black holes. Although no active galactic nucleus has been detected within this galaxy, the presence of a central black hole is strongly theorized based on models of galactic evolution. Such black holes are often integral to a galaxy's life cycle, influencing the movement of stars and gas in the inner regions and regulating star formation through their gravitational pull. Moreover, the bar structure itself acts as a mechanism for redistributing angular momentum within the galaxy. This redistribution can lead to the gradual migration of stars and gas, shaping the long-term evolution of the galaxy's morphology. NGC 1300's bar is particularly notable for its length and prominence, making it an ideal subject for studies focused on the lifespan and eventual dissolution of these features in spiral galaxies. High-resolution images of NGC 1300 have also uncovered faint stellar streams and other evidence of past interactions with smaller satellite galaxies. These features suggest that, like many other galaxies, NGC 1300 may have undergone episodes of minor mergers or gravitational encounters, which have contributed to its current form. Such interactions are key to understanding how galaxies grow and evolve over cosmic time, building up their mass and altering their structure. The environment surrounding NGC 1300 in the Eridanus constellation is also of great interest. This galaxy resides in a relatively sparse region compared to dense galaxy clusters, yet it remains close enough to other systems to experience their gravitational influence. This positioning provides astronomers with an opportunity to study how galaxies like NGC 1300 interact with their surroundings in less crowded environments, offering a contrast to the more dramatic interactions seen in galaxy clusters. The continued study of NGC 1300 has revealed an array of dynamic processes occurring within its structure. The galaxy's spiral arms, rich in both molecular gas and interstellar dust, are prime regions for the study of star formation. Within these arms, dense pockets of gas collapse under the influence of gravity, giving rise to massive star clusters that light up the surrounding material. These clusters, in turn, influence the surrounding environment through stellar winds and supernova explosions, creating a cycle of destruction and renewal that drives the galaxy's evolution. The bar of NGC 1300, stretching prominently across its center, serves as a channel for gas and dust, funneling this material toward the inner regions of the galaxy. This movement often results in the formation of a circumnuclear ring, a structure observed in many barred galaxies, including NGC 1300. Within this ring, star formation activity reaches a peak, producing a concentrated burst of new stars. These regions are of particular interest to astronomers, as they provide a window into the processes that fuel the central activity of galaxies and, potentially, their central black holes. Another fascinating aspect of NGC 1300 is its rotational dynamics. Unlike the rigid body rotation seen in smaller objects, galaxies like NGC 1300 exhibit differential rotation, where the inner regions rotate faster than the outer regions. This differential motion plays a critical role in shaping the spiral arms and maintaining their structure over time. By analyzing the rotation curves of NGC 1300, scientists can gain a better understanding of how mass is distributed within the galaxy, including the contribution of dark matter. The dark matter halo surrounding NGC 1300 is a key area of study. Although this component of the galaxy is invisible, its gravitational effects are evident in the motion of stars and gas. The halo extends well beyond the visible edges of the galaxy, influencing its overall stability and rotation. Understanding the distribution and behavior of dark matter in galaxies like NGC 1300 is essential for unraveling the mysteries of this elusive substance, which makes up a significant portion of the universe's mass. In addition to its internal dynamics, NGC 1300's interactions with its cosmic environment provide further insight into its history. Although it is not part of a dense galaxy cluster, the galaxy's proximity to other systems suggests that it may have experienced gravitational interactions in the past. These encounters can trigger tidal forces that reshape the galaxy's structure, inducing bursts of star formation or altering the distribution of stars and gas. The majestic barred spiral galaxy, sometimes referred to as this cosmic masterpiece, continues to fascinate astronomers with its intricate architecture and dynamic processes. Its grand spiral arms, radiating outward from the central bar, reveal an ongoing symphony of stellar birth and evolution. The vibrant regions of star formation within these arms are home to young, luminous stars that illuminate the surrounding gas and dust, creating striking contrasts against the darker background of interstellar space. This celestial wonders bar, a defining characteristic of many similar galaxies, serves as a gravitational conduit, guiding interstellar material toward its core. This process not only fuels the star-forming regions near the nucleus, but also sheds light on how such structures influence the long-term development of galactic morphology. Observing these mechanisms within this galactic marvel offers valuable insights into the broader behaviors of barred spiral galaxies. At the heart of this astronomical phenomenon lies a tightly wound nuclear ring, a region teeming with intense star formation. This feature, observed in numerous galaxies of its type, results from the gravitational effects of the bar channeling gas into the central regions. Such regions are hotspots for scientific investigation, revealing how material accumulates to create bursts of star formation and, possibly, feed the central supermassive black hole. This stellar island, spanning over 110,000 light-years, exhibits complex rotational dynamics. The stars and gas within the system move in distinct patterns, shaped by the bar and the unseen influence of its dark matter halo. These rotation patterns are key to understanding the distribution of mass within this galactic giant, shedding light on the hidden forces that maintain its structure and stability. Beyond its visible structure, this cosmic enigma resides in a relatively sparse region of space within the constellation Eridanus. While not part of a dense galaxy cluster, this luminous spiral likely interacts with its neighboring galaxies, influencing its evolution through subtle gravitational effects. Such interactions might have played a role in shaping the features we see today, including its prominent bar and well-defined spiral arms. This stellar titan, often called a barred spiral masterpiece, offers a stunning glimpse into the vast complexities of the universe. Its brilliant spiral arms, stretching gracefully from the central bar, seem almost frozen in time, a cosmic snapshot of galactic evolution. Yet, within these serene structures lies a chaotic dance of creation and destruction. Massive, hot stars form in dense regions of interstellar gas, only to end their lives in powerful supernova explosions, scattering heavy elements that fuel the next generation of stars. The heart of this galactic wonder, marked by a glowing nuclear ring, pulsates with energy. This ring, composed of densely packed star-forming regions, is like a galactic engine, continuously producing new stars. Scientists believe this activity is driven by the central bar, which acts like a gravitational funnel, directing gas into the inner core. This unique feature makes the galaxy a prime subject for understanding how barred spirals sustain star formation over billions of years. Interestingly, this cosmic marvel holds clues to the secrets of galactic longevity. Its bar is not a permanent feature. It is believed that bars evolve and eventually dissolve, reshaping the galaxy into a more classical spiral or elliptical form. Studying the bar in this galactic gem provides a rare opportunity to witness a transitional phase in galactic evolution. Researchers are particularly fascinated by how the bar redistributes angular momentum, affecting the orbits of stars and the flow of gas throughout the galaxy. The rotational dynamics of this spiral leviathan are equally captivating. Unlike solid objects, galaxies rotate in a way that defies simple explanations. The outer regions move more slowly than the inner regions, yet the presence of dark matter stabilizes this differential rotation. By studying the velocity curves of this astronomical icon, scientists are unraveling the influence of dark matter, which remains one of the greatest mysteries of modern astrophysics. This universal masterpiece is not isolated, it resides in a vast cosmic neighborhood within the Eridanus constellation. The faint whispers of past interactions can be seen in the subtle distortions of its outer arms and the faint trails of stars that may mark the remnants of smaller galaxies it has absorbed. These signs of cosmic encounters tell the story of a dynamic past, where gravitational forces sculpted the galaxy into its current form. Moreover, this spiral behemoth's size is breathtaking. It spans over 110,000 light-years, comparable to the Milky Way. This immense scale makes it a microcosm of the universe, offering a window into the processes that shape galaxies on a grand scale. Each observation of this celestial jewel adds another piece to the puzzle of how galaxies grow, change, and interact with the cosmos around them. This luminous galactic titan, often referred to as a cosmic labyrinth of stars and dust, captivates not only with its mesmerizing beauty but also with the stories it tells about the universe's grand design. The spiral arms of this celestial marvel, adorned with star-forming regions and glowing clusters, appear almost like rivers of light flowing outward from the galactic center. Each arm is a testament to the forces of gravity and motion, which sculpt the galaxy's intricate structure over billions of years. What makes this barred spiral phenomenon even more fascinating is its ability to balance chaos and order. The bar, stretching boldly across its core, is not merely a decorative feature but a dynamic powerhouse. This structure channels gas inward, creating a bustling hub of activity in the nucleus, while simultaneously affecting the spiral arms. This process shapes the galaxy into the perfect blend of symmetry and complexity, a hallmark of a mature barred spiral galaxy. Within the glowing center of this stellar colossus lies a nuclear ring that bursts with youthful stars. These concentrated regions of intense star formation are fueled by gas funneled into the core by the bar's gravitational influence. The interactions between the bar, the ring, and the surrounding spiral arms create a rich tapestry of activity that astronomers study to uncover the secrets of galactic metabolism, the rate at which galaxies consume gas and form stars. Beyond its striking visual features, this universal giant serves as a natural laboratory for studying dark matter. The unseen halo surrounding the galaxy provides the gravitational glue that holds its luminous components together. Without dark matter, the galaxy's outer arms would spin apart due to their incredible speeds. By examining the motion of stars and gas in this stellar titan, researchers are gaining deeper insights into the elusive substance that makes up most of the universe's mass. Adding to the intrigue of this celestial spectacle is its location within the constellation Eridanus, where it resides in a relatively quiet but not isolated patch of the cosmos. Surrounding galaxies leave subtle imprints on its structure, offering clues about past gravitational encounters. These interactions may have triggered bursts of star formation or subtle shifts in the galaxy's structure, contributing to the majestic form we see today. On the edges of this spiral marvel, faint trails and distortions hint at a dynamic history of mergers and accretions. These faint features are like cosmic fingerprints, telling a story of smaller galaxies that were consumed over millions of years. Such events are key to understanding how larger galaxies, including this barred spiral giant, grow and evolve through the cosmic ballet of interactions. The immense scale of this stellar masterpiece, often referred to as a galactic titan, is matched only by the complexity of the processes within it. Stretching over 110,000 light-years across, this barred spiral colossus is a vibrant ecosystem of stars, gas, and dark matter. Its spiral arms, like flowing rivers of starlight, are shaped by density waves that propagate through the galaxy, compressing gas and dust into regions where stars are born. These arms are more than just aesthetic features, they are dynamic sites of stellar evolution, where the interplay of gravity, motion, and matter creates dazzling patterns of light and energy. The bar, a defining feature of this cosmic marvel, serves as a critical driver of its internal dynamics. Extending through the galaxy's center, the bar acts like a gravitational engine, redistributing gas and stars. It funnels interstellar material into the core, feeding the central regions and potentially sustaining the activity of a supermassive black hole. Although this black hole remains hidden from direct observation, its presence is inferred from the galaxy's overall structure and the movement of stars near its nucleus. The nuclear ring within this celestial labyrinth is another highlight of its dynamic nature. This tightly packed region of active star formation is thought to be fueled by the bar's influence. The gravitational forces at play concentrate gas into the central regions, creating a fertile environment for the birth of massive, short-lived stars. These stars emit intense ultraviolet radiation, lighting up the surrounding gas and creating the glowing rings and patches observed in high-resolution images of the galaxy. This spiral wonder is also a fascinating subject for studying the influence of dark matter. While its luminous features are breathtaking, the hidden dark matter halo is what holds the galaxy together. Without this invisible mass, the outer regions of the galaxy would not rotate at the speeds observed. By analyzing the motion of stars and gas within the galaxy, scientists can map the distribution of dark matter, gaining critical insights into one of the universe's greatest mysteries. The cosmic history of this galactic marvel is written in its structure. Faint distortions in its outer arms and the presence of tidal streams suggest a history of interactions with smaller galaxies. These gravitational encounters leave behind subtle signatures, such as warped arms or faint trails of stars, which astronomers use to reconstruct the galaxy's past. Each merger or interaction adds to the richness of its structure, contributing to the majestic form we see today. Beyond its internal processes, this barred spiral galaxy is part of a larger cosmic tapestry. It resides in the Eridanus constellation, a region known for its diverse population of galaxies. Though it is not part of a dense galaxy cluster, its interactions with nearby systems influence its evolution. These interactions can trigger bursts of star formation or alter the distribution of stars and gas, shaping the galaxy over billions of years. The sheer scale and complexity of this spiral masterpiece make it an invaluable subject for astronomers. Its well-defined bar and spiral arms, active star-forming regions, and dynamic interactions with its surroundings offer a glimpse into the forces that shape galaxies across the universe. Every observation of this stellar titan adds another layer to our understanding of how galaxies like it evolve, interact, and adapt over cosmic time. This galactic marvel, often described as a cosmic colossus, offers an infinite reservoir of mysteries waiting to be unraveled. Its spiral arms, stretching like graceful bridges between the outer edges and the central bar, are home to some of the most dynamic and vibrant star-forming regions in the known universe. These arms are sculpted by density waves, large-scale gravitational phenomena that compress gas and dust as they propagate, triggering the formation of young, massive stars that illuminate the surrounding regions in hues of blue and white. The central bar of this universal masterpiece is not merely a static structure but a living, evolving feature. This bar acts as both a channel and a regulator, directing material inward while redistributing angular momentum outward. This constant flow of interstellar gas provides the fuel for the galaxy's star-forming regions and sustains the activity in its nuclear ring, a zone where the gravity and turbulence creates of stellar activity. Observing this process in such detail allows scientists to piece together how bars in galaxies like this one form, evolve, and eventually dissolve. One of the most intriguing aspects of Titan lies in its hidden heart. While the central region appears bright and active, it may harbor a supermassive black hole, an enigmatic feature that could govern the dynamics of the galaxy's nucleus. Although there is no evidence of an actively feeding black hole in this barred spiral giant, its gravitational influence could subtly shape the motion of stars and gas within the inner regions. Studying this potential feature can reveal how objects interact with their host galaxies over time, shaping their growth and evolution. The outer edges of this celestial giant also hold secrets about its past. Faint tidal streams and distorted structures suggest that it has experienced gravitational encounters with smaller galaxies or intergalactic clouds. These interactions may have left scars on its structure, subtly or triggering formation. These clues offer a galaxy's evolutionary, showing how it has acted through interactions over years. In addition to its science location in a fast neighborhood, surrounded by a collection, it is environment as it gravitations with neighboring synapses can affect spiral arms and of its the rate of star formation interconnects how galaxies related entities but are twined with their of this galaxy also unset govern its matter substance that perversely significant spiral. Without the stabilizing influence of a massive dark matter halo, the galaxy's outer regions would not be able to maintain their rapid rotation. By analyzing the motion of stars and gas in the galaxy, astronomers can map the distribution of this mysterious substance and better understand its role in shaping the universe. This cosmic jewel's size alone is awe-inspiring. Spanning over 110,000 light-years, it rivals the Milky Way in scale and complexity. Its grand structure, from the luminous central bar to the sweeping spiral arms, serves as a natural laboratory for studying the processes that drive galactic evolution. Every observation of this spiral giant reveals new layers of complexity, helping scientists answer fundamental questions about the origins and fate of galaxies across the cosmos. This galactic titan, a sprawling cosmic tapestry of stars, gas, and mystery, is a playground for astronomers seeking to understand the forces that shape the universe. Its spiral arms, glowing with the light of newly formed stars, tell the tale of an ongoing cosmic ballet. These arms, rich with molecular gas and interstellar dust, are not static, they constantly churn and evolve, shaped by density waves that ripple through the galaxy. As these waves compress the gas, they create stellar nurseries where stars of all sizes are born, illuminating the galaxy like scattered jewels. The central bar of this celestial masterpiece is a dynamic and transformative feature. Acting as a galactic highway, it channels gas and dust inward, fueling the active core and potentially feeding the supermassive black hole thought to reside at the heart of the galaxy. The bar's gravitational influence also orchestrates the flow of material in the spiral arms, ensuring the galaxy maintains its symmetrical beauty. The sheer scale of this bar, stretching tens of thousands of light-years, makes it a dominant and mesmerizing feature, a bridge between the galactic core and its sprawling outskirts. At the very heart of this barred spiral giant lies a nuclear ring, a glowing, active hub of star formation that serves as a cosmic engine. This ring is where gravity and turbulence collide, concentrating vast amounts of gas into regions dense enough to ignite the birth of stars. The stars in this region are often young and massive, their intense radiation lighting up the surrounding gas clouds and creating a spectacle visible across millions of light-years. Observing this region helps astronomers understand the mechanisms behind intense starbursts and the life cycles of galaxies. Beyond its striking visible features, this galaxy holds a secret, the hidden realm of dark matter. While its stars and gas form the visible structure, they are merely the tip of the iceberg. Encasing this spiral beauty is a massive halo of dark matter, invisible to telescopes but essential for the galaxy's existence. This dark matter provides the gravitational glue that holds the galaxy together, preventing its outer edges from flying apart despite their rapid rotation. Studying the motion of stars and gas within the galaxy allows astronomers to map the distribution of this mysterious substance and explore its role in shaping cosmic structures. But this barred spiral isn't just a solitary wonder, it is part of a larger cosmic web. Its location in the constellation Eridanus places it in a sparsely populated region of the universe, yet it is not alone. Neighboring galaxies, some visible and others faintly detectable, interact with this galactic giant through gravitational forces. These interactions, whether past or present, leave subtle imprints on its structure, from distorted spiral arms to faint streams of stars that hint at ancient mergers. These clues offer a glimpse into the galaxy's dynamic past, a history written in the stars themselves. On the fringes of this cosmic giant, faint distortions in the spiral arms and wisps of tidal debris tell the story of a galaxy shaped by time and interaction. These remnants are the echoes of encounters with smaller galaxies, events that added mass to this spiral titan and contributed to its stunning complexity. Such mergers and accretions are common in the universe, illustrating the interconnectedness of galaxies and their shared evolutionary journeys. This barred spiral marvel is more than just a visual spectacle, it is a cosmic laboratory where the forces of gravity, motion, and energy come together in a delicate balance. Its intricate structure, from the glowing core to the sweeping arms, provides astronomers with invaluable insights into the mechanics of galactic evolution. Every star, every stream of gas, and every faint tidal remnant is a piece of a puzzle that tells the story of how galaxies like this one grow, adapt, and thrive in the ever-changing universe. This galactic titan, sometimes called a celestial symphony of light and motion, continues to amaze with its endless layers of complexity. Its sweeping spiral arms, sprawling outward like vast bridges through the void, are not only beautiful but essential to understanding how galaxies like it evolve. These arms are the sites of constant transformation, where the raw ingredients of the cosmos, gas, dust, and dark matter, combine to create new generations of stars. The interplay between gravity and motion within these arms results in an ever-changing cosmic dance that has persisted for billions of years. At the core of this spiral giant, the bar serves as a mechanism of cosmic engineering. This elongated structure is not just a static feature but a living, dynamic force within the galaxy. It acts as a gravitational conveyor belt, pulling material inward toward the central regions. This inflow of gas feeds the nuclear ring, a zone of intense star formation near the galaxy's center. Here, massive stars are born in rapid succession, their short lives punctuated by brilliant supernova explosions that enrich the surrounding gas with heavy elements. These elements will eventually form the building blocks of planets, moons, and possibly even life in distant star systems. The nuclear ring, glowing like a halo around the galaxy's heart, is one of its most fascinating features. It is a region where the forces of compression and turbulence collide, creating perfect conditions for the rapid birth of stars. Observing this process in such detail provides astronomers with a rare opportunity to study the mechanisms behind galactic starbursts, moments of intense star formation that shape the character of a galaxy over time. In this ring, the interplay between gravity and gas density creates a self-sustaining cycle of stellar creation and renewal. Beneath the visible beauty of this spiral masterpiece lies the invisible hand of dark matter. Encasing the galaxy is a massive dark matter halo that plays a critical role in its evolution. While this dark matter cannot be seen, its effects are profound, shaping the rotation curves of the galaxy and holding its luminous components together. Without the stabilizing influence of dark matter, the galaxy's delicate structure would unravel, and its outer arms would spin apart into the cosmic void. The study of this hidden component provides a window into one of the universe's greatest mysteries, the nature of the unseen matter that dominates its mass. The outer regions of this galactic marvel tell another story, one of cosmic interactions and ancient collisions. Faint distortions in its spiral arms and barely visible tidal streams suggest a history of encounters with smaller galaxies. These interactions, though subtle, have left permanent marks on the galaxy's structure, warping its outer edges and possibly triggering bursts of star formation in the past. Each of these encounters is like a chapter in the galaxy's life story, a record of how it has grown and adapted over billions of years. This barred spiral beauty resides in a relatively quiet part of the universe, within the constellation Eridanus. However, its cosmic neighborhood is not without influence. Gravitational forces from nearby galaxies, even those far removed, can subtly affect its shape and motion. These interactions remind us that no galaxy exists in isolation, instead, each one is part of a larger cosmic web, constantly influenced by its surroundings. The sheer size of this galactic wonder, spanning over 110,000 light-years, makes it an awe-inspiring subject for study. Its scale, comparable to that of the Milky Way, allows scientists to investigate processes that occur on both local and cosmic levels. From the tiniest star-forming regions within its arms to the grand sweep of its dark matter halo, every aspect of this galaxy contributes to our understanding of the universe. This cosmic titan is not just a static entity frozen in time, it is a living system, constantly changing and evolving. The cycles of star formation, the movement of gas through its spiral arms, and the gravitational interactions with its surroundings all demonstrate the dynamic nature of galaxies. Each observation of this barred spiral masterpiece adds a new piece to the puzzle of how galaxies like it form, grow, and thrive over the lifetime of the universe. When compared to other galaxies, this barred spiral giant stands out as an exemplar of complexity and harmony in galactic evolution. Unlike the simpler elliptical galaxies or irregular systems scattered across the cosmos, this galactic masterpiece showcases the intricate dynamics of a well-developed spiral galaxy with a central bar. These characteristics place it in a class of galaxies that serve as essential models for understanding how structure, motion, and energy interact over billions of years. One fascinating comparison can be drawn between this cosmic giant and our own Milky Way galaxy, which also features a central bar and sprawling spiral arms. While both galaxies share many structural similarities, such as the presence of star-forming regions and a likely supermassive black hole at their cores, each exhibits unique variations that make them valuable for study. For instance, the bar in this galactic titan is particularly prominent, suggesting it might be at a later stage in its evolutionary life cycle compared to the Milky Way. This raises questions about the lifespan of bars in spiral galaxies and their role in shaping long-term galactic dynamics. Another intriguing aspect is how this barred spiral compares to galaxies without bars. Spiral galaxies lacking bars tend to distribute gas and stars more evenly, while those with bars, like this one, create a more directed flow of material toward the core. This difference significantly impacts star formation and the growth of central supermassive black holes. In this barred beauty, the bar acts almost like a cosmic engine, driving material inward and fueling the intense activity observed in its nuclear ring. By studying these contrasts, astronomers can better understand the various pathways galaxies take as they evolve. This spiral wonder is also an excellent example of a grand design galaxy, a term used to describe systems with highly symmetrical and well-defined spiral arms. Such galaxies are thought to be influenced by large-scale density waves, which create the stunning patterns we observe. In contrast, flocculent spiral galaxies have less organized and patchy arms, making them appear more chaotic. The symmetrical nature of this galaxy's arms suggests that it has experienced relatively stable conditions, allowing these density waves to shape its structure over time. However, faint tidal distortions hint that even this seemingly serene giant has a dynamic past filled with interactions and changes. Cosmic West galactic titan also plays a role in its evolution. Unlike galaxies located in dense clusters, where interactions are frequent and often, this spiral resides in a region, allowing it to maintain its structure. In this, gravitational interactions with neighboring systems have likely influenced its form. These subtle encounters, often stretching over millions of years, contribute to the galaxy's story, shaping its spiral arms, triggering star formation, and possibly altering the trajectory of its bar. Interestingly, this barred spiral galaxy is also a key player in the study of galactic feedback processes. Feedback refers to how energy and matter expelled by stars and black holes impact the surrounding environment. In the case of this galaxy, stellar winds, supernova explosions, and potentially even outflows from its central black hole interact with the surrounding gas, regulating star formation. This delicate balance ensures the galaxy doesn't burn through its gas too quickly, allowing it to sustain star formation over billions of years. The study of this cosmic marvel has also shed light on the fate of galaxies with bars. While the bar is a prominent feature now, it is not permanent. Over time, the redistribution of angular momentum and the inflow of material may weaken the bar, eventually causing it to dissolve. This transformation could lead to a more traditional spiral galaxy or even an elliptical form, depending on external influences such as mergers or interactions. Observing this barred titan provides astronomers with a snapshot of a galaxy in transition, offering clues about the long-term life cycles of barred spirals. This grand barred spiral, a cosmic symphony of light and motion, invites speculation about its future and the larger story of its role within the evolving universe. Like all galaxies, this one is not static. It is a living entity shaped by time, gravity, and its surrounding environment. While its current structure is dominated by the bold bar and sweeping spiral arms, its ultimate fate may look vastly different, offering tantalizing clues about how galaxies transform over cosmic timescales. In the far future, the bar at the galaxy's center, now a striking and dynamic feature, may begin to fade. Bars are not permanent, they are thought to evolve over billions of years, gradually dissolving as the redistribution of angular momentum reshapes the galaxy. As stars and gas migrate outward from the bar, its structure could weaken and give way to a more classical spiral shape. Alternatively, external influences such as interactions with nearby galaxies could accelerate this process, further disrupting the bar's stability and possibly triggering a major reorganization of the galaxy's structure. The spiral arms, too, are in constant motion, slowly changing as density waves move through them. Over time, as the gas supply dwindles, these arms may become less pronounced, fading into a more uniform disk. This would mark a significant shift in the galaxy's life cycle, as star formation slows and it transitions into a quieter, more stable phase. Such a future reflects the natural aging process of galaxies, where periods of intense activity eventually give way to calmer, less dynamic states. This galactic masterpiece is also part of a much larger narrative, the evolution of the universe itself. As the cosmos continues to expand, the space between galaxies grows, making interactions less frequent over immense timescales. However, for this barred spiral, its relative proximity to other galaxies means it may still experience gravitational encounters in the distant future. These encounters could lead to dramatic mergers, reshaping the galaxy entirely and forming a new, larger system. Such mergers are common in the universe and often lead to the formation of elliptical galaxies, giant, featureless structures dominated by older stars. At the galaxy's core, the presence of a supermassive black hole adds another layer of intrigue to its future. While currently dormant or relatively inactive, this black hole could awaken if enough gas and material are funneled into its vicinity. Such activity would transform the galaxy's nucleus into a quasar or active galactic nucleus, emitting intense radiation altering the surrounding environment. Even in its current state, the black hole subtly influences the motion of stars and gas near the core, acting as a gravitational anchor for the entire system. Beyond its internal evolution, this barred spiral is part of the cosmic web, a vast network of galaxies, clusters, and filaments that stretches across the universe. Its interactions with this larger structure provide insights into the role of individual galaxies in shaping the universe's overall architecture. For instance, the faint tidal streams and distorted features in its outer regions suggest past mergers or accretions, events that contribute to the growth of galaxies and the redistribution of matter on a cosmic scale. The study of this galactic wonder also raises questions about the long-term behavior of dark matter. Encased in an invisible halo of dark matter, this galaxy relies on this mysterious substance to maintain its structure and rotation. As our understanding of dark matter deepens, astronomers hope to uncover how these halos evolve and interact with the visible components of galaxies. This could lead to groundbreaking discoveries about the fundamental forces that govern the universe. Ultimately, this barred spiral is more than just a single galaxy, it is a window into the mechanisms that have shaped the cosmos for over 13 billion years. From the intricate dynamics of its bar and spiral arms to the hidden influences of dark matter and the potential of future mergers, every aspect of this galaxy tells a story of creation, transformation, and the ongoing dance of matter and energy in the universe. The deeper we dive into the story of this magnificent barred spiral galaxy, the more profound its connection to the cosmos becomes. Its role is not just that of an isolated star system, but as an active participant in the grand drama of universal evolution. From its bar and spiral arms to its hidden dark matter halo, each component is a piece of a larger puzzle that reveals the intricate relationships between matter, energy, and time. At the heart of this galaxy lies its most enigmatic and powerful feature, the supermassive black hole. Though it remains quiet now, it holds the potential to dramatically alter the galaxy's fate. If sufficient gas and dust are funneled into its gravitational pull, perhaps through a future galactic interaction, the black hole could erupt into activity, transforming the galaxy into a quasar. This phase would be marked by the release of intense jets of energy, capable of affecting star formation across the entire galaxy. Such phenomena highlight the incredible influence of these cosmic giants, even when their presence is invisible. The bar itself, a cosmic sculpture of structure and motion, is a temporary yet transformative feature. Studies of galaxies like this one suggest that bars are a middle chapter in the life story of spiral galaxies. They form when gravitational instabilities cause stars and gas to align into elongated shapes, redistributing angular momentum and creating the intricate patterns seen in the spiral arms. Over time, however, the bar may dissipate, leaving behind a more uniform disk. Observing this barred galaxy offers a snapshot of this transitional phase, revealing how galaxies shift between states over billions of years. One of the most fascinating aspects of this galactic masterpiece is its potential for future interactions. While it currently resides in a relatively quiet region of the universe, its gravitational pull ensures it remains connected to other galaxies in its vicinity. Future encounters with smaller galaxies or intergalactic clouds could trigger a cascade of changes, from bursts of star formation to the eventual merger of systems. Each interaction would add to the galaxy's mass and complexity, further enriching its already intricate structure. Even now, the outer edges of this spiral wonder bear the marks of its dynamic past. Faint tidal streams, barely visible against the darkness of space, suggest that this galaxy has absorbed smaller systems over time. These mergers, while subtle, are essential to the growth of galaxies, allowing them to accumulate stars, gas, and dark matter. These events leave behind not only structural scars but also a story of survival and adaptation, as the galaxy integrates these new components into its overall framework. This barred spiral's role in the larger cosmic web is another layer of its significance. As part of this interconnected network of galaxies and filaments, it contributes to the flow of matter and energy across the universe. Gravitational interactions between galaxies within this web help shape their evolution, guiding the formation of stars and the distribution of dark matter. This galaxy, like all others, is both an individual entity and part of a much larger system, illustrating the dual nature of the universe as both fragmented and unified. The interplay between visible and invisible matter in this galaxy is another profound mystery. Its luminous stars and glowing gas are merely the surface of its existence. Encased within a vast dark matter halo, this galaxy's structure and stability are deeply tied to forces we cannot see. Dark matter, though elusive, provides the gravitational framework for the galaxy's rotation and growth. Without it, the spiral arms and bar would not hold their shape, and the galaxy would collapse under its own motion. The future of this galactic titan, like all galaxies, is one of inevitable change. Over billions of years, its gas will be consumed or expelled, its star formation will slow, and its structure will shift. Whether it evolves into a more traditional spiral galaxy,